is Amin. I'm going to present this project with this big, long name. The keywords are regression, particulate matter, climate, and dust storms. State of Arizona gets a lot of dust storms every year. And I've done some frequency analysis for the dust storms from 1996 up until present, and I think the present was last year that I did this frequency analysis. Most of the dust storms are happening in July and August, and that's because we have monsoon season in July and August. And when we have a dust storm, there's a high concentration of dust in the air, which we name them particulate matter. And they are in two classes: particulate matter less than 2.5 microns and particulate matter less than 10 microns. And if you want to get some idea of how small these particles are, we can compare them to human hair. This is the blue ones are PM10 and the red ones here are PM2.5. So they're extremely fine. The goals that we had in this project, or I had in this project, is first goal is to simulate climatic parameters like temperature, wind speed, and a bunch of other variables that I will discuss later, and also particulate matter PM10 and PM2.5. Then using those data, we were going to develop regression models, and we tested two regression models: ordinary least square and also GWR, geographically weighted regression. So the first one is just a classic regression model, and the second one is more spatial and suited for our purpose. The model that we use for simulation is called WRF, or Weather Research and Forecasting. It's very popular in atmospheric hydrology. Using this model, we can simulate climatic parameters, temperature, wind, and also some Earth or parameters like soil moisture or a bunch of other parameters which were very useful for us in our past research. If you use this simulation model with some other modules, which one of them is a chemistry module, you're also able to model the dispersion of constituents in the atmosphere. In our case, we were using that for PM10. We deployed WRF-Chem in Northern Arizona University's cluster computer, which is called Monsoon. And that was actually the reason why we were able to do this project, because you cannot run WRF on normal computers. You need a lot of memory and a lot of storage. And this cluster has 600 CPUs and GPUs. Not sure how many GPUs, but 600 cores. Our study area is the state of Arizona, because the state of Arizona gets a lot of dust storms. And we needed case studies to study particulate matter. We used National Oceanic and Atmospheric Administration's website to locate the dust storms that to identify the dust storms that happened in the past years. And you can see here there's an option for dust storm, dust level, debris. These are all dust storms. They're just different in the shape and in the intensity. And also we used media. Some of the dust storm gets a lot of media attention. And we were able to select 9 dust storms, one for each year, 2009 to 2016. And we chose 2 for 2014 because they were 2 very huge dust storms in 2014. And the variables that we chose for our study was from past literature review. And most of the literature review, they were focusing on 2 or 3 variables. We have 11 variables here, including the dependent and independent variables. We had this flexibility because we get all these variables out of WRF. And so some of the variables that we have, they came as 4D, latitude, longitude, elevation, and time. And some of them came as 3D, latitude, longitude, and time. So we had to post-process the 4D variables to change them to 3D. For example, PM10, the one that we are interested in is the PM10 close to the Earth, right? We are not interested in PM10 concentration in third layer of atmosphere or somewhere close to 50 pressure. The layers in atmosphere are based on pressure. And then we divided our variables to 2 categories. The main variables, height, temperature, wind speed, and vegetation fraction. and the supplementary variables or secondary variables, which is pressure, planetary boundary layer, and soil moisture. And if you have any questions about each one of them, I'm happy to answer after the presentation. I don't think I have time to define them one by one. And so this is just for 2014 case. You can see the height, which is just simply topography. So closer to boundaries here, we have 0 height because we are closest to the ocean. And here in Flagstaff, we have a higher height. Temperature close to Phoenix and Tucson, we have a higher temperature at that season compared to Flagstaff. U10 and V10 wind speed in different directions. I can see some clustering for these wind speeds, but I'm sure if you change the months, they will be different. Vegetation fraction, which shows where you had more vegetations. It's close to, again, Flagstaff, we get more vegetations, and here we get more vegetations on the eastern side. Then PM10 concentration, huge PM10 concentrations close to Yuma, this side of Arizona. And then the secondary variables like pressures, these two pressures, the only thing that you need to know, if you sum them up, you get atmospheric pressure. And planetary boundary layer, which is really difficult to calculate and characterize, and soil moisture, which you see the highest soil moistures here on the northeastern side. So with WRF-Chem, we were able to simulate our PM10, and we were also able to average it for census tracts. You see that the huge PM10s are happening in these regions for most of the case studies, and the allowable limit of PM10 from US EPA is 150 micrograms per cubic meters, and from EU is 50 micrograms per cubic meter, and we had very huge PM10s. This is what we expected because in dust storms we get very huge PM10s. This one, case study 2, has 17,000 micrograms per cubic meter, which is huge, and it's a health problem. So any numerical model should be accompanied by validation. We were able to get PM10 data from Pinal County. These are measurements. You see dots here. These are all measurements from Pinal County. They are hourly measurements. And the green line is our simulation from WRF-Chem. Our correlation coefficients were good. This is good for atmospheric science. And if you see a pulse in PM10 concentration, this means we had a dust storm here. So for example, this one is July 5th, 2011. This is case C in our case studies. And the other one, 2014, is also here. So you see 2 pulses here, 2 back-to-back dust storms we had. They were smaller than this case. So then using that data, we developed some OLS, ordinary least square regression. And you see the governing equation for OLS. You see them in bold because they are vectors. So dependent variable, in our case, it was PM10. We also did it for PM2.5, but we didn't report it. And then we have independent variables, which were our climate variables in this case. Then you have some coefficients to optimize this equation, and none of the equations are ideal, so you're going to get some error or residual. So on the right, you can see all the case studies, A to I, with their determination coefficients, which is pretty good, 0.92, 0.85, 0.75. And based on all these case studies, we were able to recommend this general equation for PM10 in the state of Arizona. And since this equation needs 1, 2, 3, 5, and plus 4, 9 independent variables, it may not be practical to use this equation. So we removed the secondary variables. We still got good correlation coefficients for this model. So it's more practical because height, temperature, wind speed, and vegetation fraction, these are always available. Then for GWR, it's the same equation as OLS. The only thing which is different is in GWR, you are using that equation for every feature separately, and you're considering the neighborhood of each feature. And you need to have some weight metrics or some distance decay function that we used in this study. And it just simply says that if your feature is within some threshold, it gets attention from the nearest neighbors. It doesn't get a lot of attention from the furthest away. So it's kind of like the first law of geography that if something is closer, it's more related. And I had a time to just go over your comments last night. I came really late last night, and I saw that you requested this bandwidth. So I went back and I realized that the bandwidth that I have in my studies is 1.5, but I don't have time to find out which unit is. So I'm going to ask that question later from you. Okay, so let's go over the distributions. The height distribution is higher in, I can see that it's higher, it's more red close to Phoenix. Temperature distribution is pretty clustered here. And the residuals and R-squared. The R-squared, we were able to increase R-squared to 0.96. And the lowest R-squares are happening close to the boundary, which I made this assumption that it's probably because we don't have enough neighbors for each feature close to the boundary. That's why the R-square is not really high. The residuals looks random to me. Well, I'm going to read your comments one more time, but they look pretty random to me here. But in order to make sure that our residuals were completely random and they're not clustered, I did a spatial autocorrelation local Moran's-I analysis, which we have high, if a high feature is accompanied by another high feature, it's clustered. The same for low feature and low feature. But if a low feature and high feature are together, they're just outliers. So for OLS, which is on the left, I see a lot of high, high, and low, low. And they are like 47% of the area. For GWR, it's better. It's close to 16%. So I believe OLS should be used like initial method just to study the variables, and GWR because PM10 is very spatial phenomena. So I think GWR works very well for PM10 concentration. Then the applications with this regression model, it's a very simple PM10 model compared to simulations that we did in BARFChem, which takes days because it needs a lot of memory, it needs a lot of skill. You have to use Linux. You have to code in WRF. So this simple model is very simple to use for prediction. Using that model, we can develop risk maps like hotspot, cold spot analysis, and warn people with health problems not to go outside in high risk times. And we can also use this model to forecast. We have some climate models that gives you the temperature and other climatic indicators up until year 2100. So combined with this regression model, we can forecast PM10 up until 2100. So we can do all sorts of climate change analysis and all those things. So it's good for forecast, and we use this open source BARFChem software, which can be used everywhere in the world. The only thing that you have to do is just you need to calibrate your model. You have to come up with those coefficients, which I believe should be different for any region. The limitations that we had in our project, we realized that since we are using census tracts as our polygons, there are a lot of empty census tracts close to Phoenix and Tucson because there's a high density of census tracts over there. And although our model had a very good resolution, but some of these census tracts were really small, so we were not able to average some PM10 for these census tracts. So we removed this in our analysis, but I think there's some error involved in this analysis. So this is the first one. The second problem is the impact of resolution and projection. So the resolution that you get in your simulation, we used a very high resolution. The temporal resolution was really high. It was 45 seconds. That's the reason that you're able to capture those dust storms. The spatial resolution was 7 kilometers. It was good, but still, I'm not sure what the impact of resolution is. The validation of PM10 told us that the resolution we chose was good, but still, I believe there should be some sensitivity analysis to quantify the impact of resolution. Then land use. We didn't use any land use in our regression, but we used soil moisture and vegetation fraction because we were not able to use land use because the land use was one of those nominal data types. So it was 1 to 20. So 1 was sand, 2 was grass, 10 was shrubs. So we were not able to use this in regression. You can't use this type of data in regression. So that's another limitation, but we used vegetation fraction and soil moisture instead of land use. Then the numerical validation, we validated our dependent variable, but we didn't validate our independent variables because there are like 9 of them, and it was a different project to validate them separately. Then the limited number of case studies, we had only 9 case studies, so maybe they are not random. Maybe if you choose different case studies, you get different results. So this is another limitation. What we are focusing right now, we are focusing in developing a land use model, combining vegetation fractions, soil moisture, and land use in one big function that can be used in PM10 analysis. That was my presentation. So if there's any questions, I'd be happy to answer.